and start the record. So find the vertex form for f of x equals 3x squared minus 24x plus 51. And so if you want to find vertex form, what's the first thing you should probably find?
H.
Yeah. I was looking for the more like obvious, like the vertex. You need to find the vertex for the vertex form. So the H is the x component of vertex. You find that guy first. Yep. Ooh. Remember that one?
So
how to use it a few times.
What? I was say, do you want us to say the vertex, or
Yeah,
do you just want H?
What's the formula?
So it's gonna be A parentheses X minus H parentheses plus K.
Just the H.
For H?
Yeah.
Oh, I'm sorry. Negative B over 2A.
Yeah.
My bad.
So we're going to find out what our x coordinate is with the H is equal to minus B over 2A. So this is one of those things. I don't really like telling you how to memorize things a whole lot. But this might be one of those things you have to kind of memorize. And we'll, like, hopefully you've used it enough yesterday and in your homework and in the notes to sort of get a grasp of minus B over 2A. So minus B over 2A, I think, is over 2 times
equals 4.
Yeah, so we're positive 24. This is what that's going to be. Finishing that is 4. Looks good. Okay. Now, how do I figure out my K?
Oh, you plug 4 in?
Plug 4 in to F. So 3
equals 3.
This is all going to be 8 minus plus 51. So these are not the prettiest numbers. Is that right?
First one should be 48.
48, yeah. So definitely double checking my solution. Did I get this right? Yes. Okay. So I should be getting 3 for this thing. So what is my vertex? And I'm already cramming it into my other problem.
It's 4, 3.
4, 3. 4, comma 3.
And when we get to where they learn the quadratic formula, then that negative opposite B over 2A totally will make sense to them. So I always feel bad about having them memorize stuff too, but it's kind of like you'll learn why that works in a later lesson.
Okay, so our formula looks like x minus h plus k. So if I'm doing the x minus, what number am I putting here?
Putting in the 4.
4 here. And it says plus k, so I'm putting plus
3.
3 on the outside.
Would we put the A back in that equation?
And we absolutely have to do that. So we're bringing down this A that we started with was a 3.
Right.
We're bringing this guy down right in front of the square. Okay, so this is my sort of formula. If I say find any min or max of f of x, well, if I'm looking at this thing, is that going to be a min or a max is kind of my first question.
I actually had trouble on this one.
would be a minimum, right? Because it's positive.
Okay, so think about what your graph looks like. It's looking like a positive parabola. That's going to have a minimum. So if we have a negative parabola, it will have a max. So if it's flipped the other way, negative will give you max. These will give you min. So it is a min value. And if I ask you what the min of f of x is, that's kind of like asking what the min of y is. So what is your y min here?
3.
Of 3. You might want to use is that the value of x equals? Sort of like what I have in my head. Okay. So this, you're just gonna have to kind of think about the direction of the parabola, whether it's giving you a min or a max. Think about your graph. Okay. Questions about this? Are you ready for the new stuff?
Let's do it.
All right. Not that one. This one over here. So there are quite a few problems in this, but they are all pretty quick, like solve this sort of radical problem. So I don't think these should take too horribly long. Let's see. There are, what, 6 problems here? I think these are straightforward. This one, there's a little rule I talked about that might help you a little bit on that one. This one is written as a decimal. How might you want to rewrite that so that it's easier to sort of solve? There might be an easier way to solve it if you rewrite it. So 0.01 is how much? Make sure we do our decimals correctly.
Geez, hold on. Sorry, I'm drawing a blank.
First is 10th. Second is
100. Thank you.
100.
Wow.
Yes. So that is 1/100th is probably the way you want to write that. Square root of 19. Oh, what did they do? And this is a calculator. Oh, those are calculator check problems. I thought they were going to actually make you do some work. But I want you to predict what it's going to be between before you plug it in your calculator. Make it a little more difficult. What number should it be between? I want you to think about that. So I'll give you just a few minutes to think about these, and then we'll start going over them, I think. Check what we got right here. Those 8.2, we get into the little more messy stuff, I guess. And the 8.8 stuff is the imaginary stuff. And I don't think we officially talk about that section where they talk about the fundamental theorem of algebra. I think they kicked that out of this class.
Yeah, they used to have it in there, but I don't think they do anymore either.
But we will still be mentioning it at some point.
Yes,
We did all this
absolutely.
work to work up to it. Like, you were going to mention that it's a thing, at least.
Yeah, it's kind of bad to teach the algebra class without
It
Going
might
over
be.
the fundamental theorem of algebra.
Yeah, that one might be slightly important. Uh, And so today we're doing cube roots and we're doing imaginary numbers. Tomorrow we're gonna like jump into cube. Did I say that? I said that wrong. Today we're doing square roots and imaginary numbers. Tomorrow we're gonna jump into cube roots.
Yep.
And then I don't think we really go much higher than cube roots. You start getting to fourths and fifths, it gets nasty.
Yeah, we'll do fourth and fifth only on like variable expressions, I think, pretty much.
They also keep insisting in the notes that the multiplication property works for like all real numbers or something like that. It's like, I'm pretty sure A and B have to be positive.
Yeah.
Because if there's eyes, you have to pluck out your eyes first. It's really important.
Yeah. You know, I don't like that either. Yeah.
Oh, man. Okay. Square root of 64. I hope this one does not take you too long. This is an even square root. What is this equal to?
8.
We take a group of 2 out. It comes out as 1. This is the square root of a minus 100. Can we do this? That's the first thing I'm going to ask. Is this doable? Ooh.
That was quiet.
Yeah, it's really quiet. Is that something that we can do? Can we take this? Crunch it?
Guess so.
We should be able to because the negative's outside of the radical.
Yeah, absolutely. That's what I was hoping y'all would recognize. The negative is not inside the radical. As long as we're taking a radical of a positive number, we can do it. Radical of 100 is, I hope it's not taking you off too long.
-10.
It's going to be 10. This is sort of like saying. It's like essentially what we're doing. There's a negative that we're tacking onto this thing. It's not in the square root. It's on the outside. It should be safe. Square root of 4/9, and I talked a little bit about this. If you wanted to try to break this up into 2 fractions, you could probably do that, but it's not the prettiest thing to do. What can I do with this radical and this numerator and this denominator? I can think of this like 1 of what?
Square root of 4 over the square root of 9.
Yeah, so I can do some distribution sort of property with this radical and this fraction. So if I see a radical of a fraction, I can split it in the numerator denominator and vice versa, right? If I have a radical over a radical, I can kind of put them together. So square root of 4, these are both even roots, so I'm hoping this doesn't take you too long. Square root of 4 is, square root of 9 is going to be 3. I guess the other way you could do it is like you have square root of 4. Like 2/3 times 2/3 if you really wanted to try to break it up with fractions, but that is not a pretty way to go about it. And we have the same thing being repeated. It would come out once as 2/3. Questions about these? Are we getting these down, hopefully? I think these are like starting with the properties of the radicals, right? Okay, the next thing is this 0.01, and I already kind of said if we want to do this, this is a negative square root, and I really want to write this as 1 over 100. And if I rewrite this as 1 over 100, I hope you notice this is, and I can write this as a negative, and this top should say what?
1.
Square root of 1. Yeah, I'm going to write the middle step in it. Square root of 1 is 1. So if I'm being honest, if you didn't write this step where square root of 1, you could probably just tell me that's 1 on top. And jump right to that 1 on top. So we have a 1 on top, and we have what on bottom now? Get out of here, Cord.
10.
There's going to be a square root of 100. It gives me 10. So this should be minus 1/10. Don't forget your negative. He's carrying along for the ride, tagging along. Okay. Questions. Oh, man. These next two are basically a calculator check problem. Round to the nearest hundredth. That is 2 decimal places. If we want square root of 19, if I were to guesstimate what this 2 numbers this is in between, what 2 numbers would that be between without a calculator? How would you know?
The 2 closest squares are 16 and 25.
We're thinking about perfect. 16 and 25. This is 4 squared and this is 5 squared. So it should be between 4 and 5. If I do square root of 19, I guess I pull that up. I'm getting like 4.36 if I round it to the nearest hundredth. 4.36. 53 would be between 7 and 8 would be what, 64? So 53 would be between what 2 numbers?
7 and 8.
7 and 8. And we get 7.28. So this is basically a calculator check problem. To be honest, I don't know if there really is a way that you're going to be able to do that easily by hand. Okay. Do we have any questions over any of these 6 problems? How to go about doing this? Okay. 8.2, we got 2 more problems. I want to look at these and get these down. So these I don't think are going to come out evenly. Radicals. And simplifying radicals that are probably not going to come out evenly. Oh, what are the instructions on it? There's no instructions. Simplify using absolute value signs as needed. Oh man, that's a. Okay, so there are a few different ways to do these problems that I mentioned in the notes. So how do you break apart 27? So the first thing we probably need to do if we're going to simplify them is factor these things out somehow. There are multiple sort of ways to factor these out. If you can factor them out in a quote unquote sort of pretty way, I think that might work to your advantage. If not, we can always just go prime factorization and start circling the groups. So how'd y'all break this apart? Y'all do 9 times 3 or 3 times 3 times 3, I think is what we're going to do. You do prime factorization. It will be what? 3 times 3 times 3? This is one way you can do it. Either way you do it, you should be getting the same result. So what am I circling now?
One pair of threes.
So I circle a pair of 3 coming out at once. So what should this end up giving me?
3 to the square root of 3.
Yeah, it should be 3 with the square root of 3. Okay, so we're looking for groups of 2 when we do squares. If we do 800, how'd y'all break 800 apart? So this one, I probably don't want to do prime factorization, although it wouldn't be too bad, probably.
Yeah, I would not recommend, but I didn't remember the other method, so.
If there's a lot of zeros in there, I'd probably focus on that first. So if I do 800, that's like what? What are 2 good numbers? And it doesn't, you don't always have to get everything out all at once either. We can break it apart into pieces if it's really big like this. But is there any sort of perfect square you might notice in 800 if we think about going back? Ooh, where did I put that paper with all my squares? Think about all our squares. They're like 25. So any of those things, are any of those things going to divide into 800? Is what we're thinking.
100 and
100?
25.
Yeah, 100 seems probably like one of the most obvious things that kind of pops out to me. Of course, I've been doing these a couple of years, but 100 is definitely gets something out of there. So if we're doing this, this is like square root of 8, square root of 100. So I talked a little bit about this property, but if it's written as like a single thing, I can kind of separate these things. Square root of 100, that's going to be what?
10.
That's going to be 10. It's like I have 10 here. And the square root of 8. I can break down a square root of 8 probably a lot easier. That's 2 times 2 times 2. So that's not too bad to break down. I still have a 10 that I'm multiplying.
Cool.
I can pull out what? What?
One set of twos.
I can pull out one set of twos. I'm gonna have a square root of 2 left over. Now what's on the outside?
20, right? You multiply the.
This is I guess is what I'm trying to say, right? Make sure you're multiplying those two things. It's gonna give you 20 the square root of 2. Okay, so if I'm seeing 20 on the outside, well, that's kind of telling me, and I've done these things a few times, so don't feel freaked out. But there's like 20 squared is going to give me 400. I could have broken it up into 400 times 2 to begin with, I think is what it's telling me. So if you really wanted to do it like the smartest way possible, right? But it may not be super obvious that this is what's in there. I don't know how to say it, right? You can pick it apart piece by piece if you have to. If we wanted to write out the prime factorization of 800, that's something you could do as well. It's just going to be a lot of numbers, and I was trying to save a little bit of time. Are there questions over this? We can look at perfect squares. We can pick out perfect squares if we can see perfect squares in there. The other thing we can do is we can write out its factorization, and if we see 3 of the same thing, we can pull it out. When things come out, they're getting multiplied out here. So we multiply things outside with things outside. We multiply things inside with things inside. We kind of keep them separate, right? And I'm hoping you're keeping these things separate in your mind a little bit. Now they ask us to simplify these things. So we are doing the same sort of thing. These are not even radicals. They want us to pull things out of these radicals. In an 83B, they're actually throwing something a little bit different at you. I don't think we've seen it. So if it looks a little weird, I don't believe we had any division in our notes, but I could be wrong.
Not that I remember.
Yeah, I don't think so. It's a little bit weird, and we'll talk about it. But if you just get these radicals and you simplify these radicals, we will talk a little bit about how to simplify part B. So I want you to work on these radicals and get these radicals done right quick. Three, 4. Okay. I'm just gonna give y'all like 1 minute on this thing, maybe 2 or 3. Oh, what happened to Michael? I thought he was here already. Maybe.
He was maybe just got thrown out accidentally.
Yeah, I mean that happens. I see your emails. I don't know. I'm not really sure what to tell y'all besides try to log back in. Sorry you have to deal with technology and issues. So 83, we are simplifying this thing is what we are doing. Are there numbers that are not real numbers and not imaginary numbers that the complex numbers can't grab? That's what I was trying to think.
Now what?
Are there numbers that the complex numbers don't grab is what I was trying to think. Because it should grab all your reals. It should grab all your imaginaries and combinations.
Yeah. It does.
So I'm trying to think, are quaternions, are those? That's a bit beyond what I know personally, quaternions.
What
I
is
know they're a
that?
thing. They're kind of like imaginary numbers,
Uh-huh.
but they're like, there's 4 of them. I don't.
Is it like
Oh, it is.
e to the pi I or something like that?
There's an I, J, and a K.
Oh.
It extends the complex numbers, is what it says.
Okay,
I
yeah,
think
I
it's
know.
still-
No, I know what you're talking about.
It's applied to mechanics in 3-dimensional
Yeah.
space, is what it says. It is used
Yeah.
quite a bit. I'm pretty sure they use it for cryptology a little bit.
Yeah, when you're talking about all those vectors.
Mm-hmm. They multiply a certain way. They're kind of weird. We don't go over them in here, so you don't have to worry about freaking out about that.
Yeah. The
They're
complex
definitely-
numbers is just the set of all reals and all imaginaries. But
Yeah.
yeah, probably there's.
Okay, so we want to go over this 5 plus radical 12. So how did you divide radical 12 up?
I used 3 and 4.
3 and 4 are good things to go with. So I have 5. Was it 5 plus this? I have 5 plus, and I'm going to look at that radical 4 kind of differently from the radical 3. If I want to separate them, I can kind of separate these things. But the reason why I'm doing this is because radical 4 is really just what number?
2.
Okay, so we have 5 plus 2. Oh, I'm so glad they did this.
Do we go ahead and add those 2?
Oh, I'm so glad you asked that.
There it is.
There it is. This is like 5. This is like 2 square roots of 3. So if you want to think about this, this is just another number. If we had something like 5 plus 2 times x, would we be able to add these things?
No.
No, because this thing does not have an x. So this can only get added if their radicals are exactly the same. So this, don't do it. Don't tell me 7 square roots of 3. That would be totally wrong.
Got it.
If we wanted to add them, and maybe giving an example where we can actually add them, they would both have to have that thing on there.
I see.
So that we have 5 square roots of 3 plus 2 square roots of 3 will give us a total of 7 of those square roots. That
So
is
the
a
radical
legitimate.
like it's a variable. Got it.
You treat it just kind of like it's a variable. Okay.
Alrighty.
Got to have like terms when you do these things. So glad this is a good question actually, because it's got this thing happening in here, and I'm so glad this question is getting asked, because you don't even know how many people miss that. Like I bet you like at least half the class was thinking that, at least.
Happy to help.
I appreciate it, man. I really do. So 10 minus square root of 24 over 2. If we want to break up square root of 24, how are you breaking up square root of 24? Let's simplify that guy first.
6 and 4.
6 and 4. So what I'm thinking is this is going to be what? 2 and a square root of 6. So maybe I'm flipping them, reversing them. The square root of 4 is giving me 2. Square root of 6 is a square root of 6. This should be 2 square roots of 6. Let's take it back to this problem. I'm doing 10 minus this. So 10 minus 2 to the square root of 6. And I'm dividing this by 2. Now this, if you did this, this is fair enough. We haven't gone over like this next thing I'm about to do. But when we add and subtract fractions, the first thing we try to do is find a common denominator, and then we add or subtract over that common denominator. So this is kind of like going exactly reverse of finding a common denominator. We have a common denominator. We can split these things back up over that common denominator. So what I have on this side looks like 10. What I have on this side is 2 square root of 6. And there are, I will go ahead and say, there are probably a few other ways you can do this and simplify this. This is probably my suggested way for y'all to go about this, because this will make it a little bit easier. I have 10 over 2 gives me 5 over here. I want to subtract. And I want to be really careful with this thing. So what would you divide over here?
I mean, I think it's just square root of 6.
It is the
If
square
you got,
root.
if you got 2 square roots of 6s and you take one of them away, you're left with square root of 6.
Yes. So we want to divide, and this is the thing I'm talking about. We want to divide things on the outside with things on the outside. So this 2 on the outside gets divided with this 2 on the outside. If you try to tell me like square root of 3 or try to change the square root at all, it's not correct. Like things on the outside with things on the outside.
And so that's really good. I think that's really important that you separate those two, because a lot of times, Matt, can you write this down? I just want to show them another mistake people make. 5 minus 2 root 6 over 2.
Oh, they'll do 5 minus 2 root 6 over 2.
No, the whole thing. 5 minus 2 root 6, the whole thing over 2.
Okay. 5 minus 2 root 6 over 2. Gotcha.
And I can't tell you how many people will just cancel those 2's.
Yes, they will see the subtraction. You have 2 terms here. You have to take 2 out of every single term is another way to do it.
Right.
You could do it that way, but you have to do it out of every single thing. So if you split it, you will end up doing that. So that's why I split things. It's because it tells you we're dividing this and we're dividing this. A lot of people will try to just divide this one thing and not get the second thing. So both of these are being divided. Do not do this. Ooh, I'm hitting stuff. Here we go.
Are we not worrying about those ones that you had scratched out?
This one?
No. The like actual homework problems, like 67A or 71A.
Those they shouldn't be in there anymore. I don't think there's like a revised. I think they got revised out is what happened. Because on this paper they don't show them. I don't believe, right?
Ah, okay.
These
I have
numbers,
the-
yeah. So maybe take note of that. These numbers are differing from these numbers, and we're going by these numbers is what I'm going by.
Okay, just want to make sure.
And there's not too many. There's a few that got rejected, I think, and like 4 that maybe got added. They're mostly the same. Okay, we got 1. Where am I at? Page 2. We did that. Okay. And there is another problem on like the notes. So we will be doing this probably again tomorrow, these sorts of things. But I think that the thing to kind of take away is when we multiply and divide, anytime you multiply and divide, things outside the root get treated with things outside the root, and things inside the root get treated with things inside the root. We want to kind of keep them separately as much as possible. When we multiply and divide, we look at them differently. So that was what, 83? Is that what we just did? Now we are on 409. Okay, so we got 3 problems to introduce us to imaginary numbers here. And so I'll give you about 3 minutes, maybe. Look at these, think about them. And it looks like we got some addition, subtraction of imaginary numbers, and then we got some multiplication of imaginary numbers. And I think we got some simplifying imaginary numbers on the last page. Yeah, that's what it is.
So this starts sounding pretty violent, because whenever you've got negatives under the radical, the first thing you always want to do is pull out the eyes.
I feel like we're just bullies in math, to be honest.
I know we are. It's like pull
We
out
always
those
wanna get
daggum
that.
eyes.
Well, that and when we solve for a variable, we always want to get him alone and by himself. It's always like, look out the eyes. Okay. So if I have a minus 16, I'm hoping like the way you're picturing this in your head is probably like I have that negative kind of separate from the 16. And so anytime you see a negative in a square root, what's like the first sort of thing? Like, I hope this is your knee-jerk response. First thing you should put is what? Square root of a -1 is going to be
I.
I. So I need my I there. The other thing I'm seeing there is a what, 16? So what is 16 going to be if I square root it?
4.
4. I don't know why I got two different colors, but this should just be 4i, right? So root positive 16 would be what? 4. Root negative 16 is going to give us 4i. So they are very sort of similar. Maybe you might notice that similarity. If we have a square root of minus 11, so this is the way I hope you're picturing things in your brain, is like we see that negative sign. That negative sign is in a square root. That is telling me to do something. That is telling me to pluck out the I. And what else do I have there?
And I couldn't do nothing with 11. I just kept it square root.
It still has a square root of 11
Yeah.
now. So I square root of 11, that is a thing. We can write it. There's no simplifying this. It's done. There is a little notation thing that I will do that the book may not do, or other books may not do. I will put my I in front of the radical. And I don't know if I mentioned this in the notes or not, but a lot of times people will write it after the radical. And the problem with that is if your radical extends too far and your I gets put under the square root, square rooting I is not the same as I. So this is changing your problem. So I will like typically plug it out in front, because when you're doing your radicals, let's be honest, we're going fast and we're just doing like that in motion. There's a good chance you're just like going to put it over other things that it shouldn't go over. So I will try to put coefficients and things out in front of the radical quite often instead of putting them behind. But the book sometimes likes to put them behind. It really should look like square root 11, just to re-emphasize, right? That's not the same thing as that. Not equal, right? So you got to be careful whether you're writing this thing or this thing, is what I'm trying to say. Square root of a -8. So first thing I want to pluck out is the negative. Takes care of that. And I still have a root 8. And I know I'm writing it there. But is that fully factored? Is it going to solve that anymore? Simplify it?
We can simplify it more.
Yeah, so root 8. And I think we did this one already today. 2 times 2 times 2. So how is this going to simplify?
I got 2i and the square root of 2.
Yes, so I'm pulling out 2 of them. I'm multiplying by I is going to give me 2i. And I'm still going to have a square root. And this guy right here is still underneath the square root. So that's coming from those two coming out from that guy. Okay. These are getting at how to simplify radicals with negatives. Now we're going to talk about adding subtraction. And so I said it in the notes, but when we deal with i's, we deal with them just like they're x's. Cut off all contact. No. Cut off all contact. Don't have thought. No. We treat them just like a variable. 1 plus 3i plus 7 plus 4i. 6 plus I minus a -2 minus 4i. So these, I'll give you a few minutes to do them, but the addition and subtraction, they should not take you, hopefully, too horribly long. When we get to multiplication, it's a little more involved, but it is the exact sort of same as multiplying variables. There's just like an extra little simplifying step that we might have to do. Okay, so what are we adding on this first one? When we look across here,
Two constants, 1 and 7.
1 and 7, so 1 plus 7 is going to give me 8, and I'm going to have plus.
And then you'll add your two i's together for 7i.
7i. 3 plus 4 will give me 7. So this, I hope, is not the confusing thing. We treat I just like it is an x. We look for like terms is the word I'm trying to look for. We look for like terms. We do 1 plus 7 is going to give me 8. That's my constants. My i's are 3i and 4i will give me plus 7i. And I did write it with constants first. So if you write your constants first and your imaginary part second, you'll be in that standard form for the complex number, a plus bi. This thing, now instead of addition, we're doing subtraction. So instead of adding, I'm now subtracting. What I'm going to do and what I usually do when I subtract is I just distribute the negative. So if I do this, this should become a plus 2, and this should become a plus 4i. And so this is really no different than the previous thing after you do that distribution. What should I be getting here?
8 plus 5i.
That's exactly it. 8 plus 5i. Okay. And I did do a few of these problems in the notes. So hopefully you know the little simplifying step that I'm talking about. But if you don't, go ahead and do these anyway. Multiply these through. I will give you all just like a minute or two to finish these things up. And let's go ahead and throw that one up there too, I feel like. Okay. So if we want to solve this, oh man, If y'all tell me 9 plus 16, I'm gonna cry. What should I do with this thing so you don't do that? There's something I told you to do with perfect squares.
Write it out twice.
Write it out twice. So write this thing out twice before you even try to solve it.
Yeah, I couldn't get it past a complex number here. So that's all I could do.
What's that again? You get a complex
437.
number?
437.
37?
Yeah.
Yeah, it should still, it should be a complex number for that solution. It's conjugates that give us weird things, right? Is that what you're thinking? Perfect square should still give you complex. Not solutions, but simplifying, yeah. Okay, so this first thing, if we do minus 6i times minus 3 minus 2i, this is a monomial times like a binomial sort of thing. We're just distributing this single thing. So the first thing that I see here is a minus 6 and a minus 3 is going to multiply to what?
Positive 18.
There's a positive 18 and there's an I attached to this guy. The next thing is minus 6i times a minus 2i is going to give you negative, and negative will make it positive.
Mm-hmm. And then 12i squared.
12i squared. Okay. And if you did this, you did a good amount of work. There is one extra little sort of thing I really need to fix. I know I is like the square root of a negative 1. I know I squared is equal to what? And this is how we kind of defined I. It's the thing that when you square it, it's going to be equal to negative 1. So we really don't want anything over a single power of I in anything that we solve. So anytime we see anything that is higher than a single power of I, we have to replace it with what we know. So instead of I squared, I can replace this with a negative 1. And this might look like 18i minus 12 might be one way you write it. But if I want to write it in standard form, I really need to swap these things around. So I'm starting with the minus 12. And sometimes this confuses people, but this is plus 18i. When I swap those things around. Okay. So looking at this thing, it is the same as if you're distributing and multiplying by stuff with variables. You treat it just like a variable. But there's an extra little step. If we have anything over a power of 1, we like an I squared, which we'll probably get quite often, we replace I squareds with minus 1. So this is like 12 times minus 1. And then just the other thing is just putting it sort of in the correct a plus bi sort of format. Okay. The next thing, 4 plus 3i minus 5 plus 6i. So this is just sort of like we had before with two binomials multiplying. Some people like to call it FOILing. But 4 times a minus 5 is going to give me what? Minus 20. 4 times 6i is going to give me plus 24i. What is next?
Negative 15i.
Yep, minus 15i. And then the last thing looks like plus
18i squared.
18i squared. And so maybe we see it, maybe not, but there is a higher power there. So there's minus 20. What do you notice about this? Are there any like terms I can combine? I think it's plus
Those middle two I terms.
9. 9i. And then we have a plus 18i squared. And I probably should have did it with this step, but I didn't do it. What else do I need to do? So plus 9i. I've been hinting at it, but I really need to change that thing. So instead of I squared, what am I going to write?
Times -1.
Times a -1. So this is like a minus 20. This is like a plus 9i. And now this is like a minus 18. And so I still need to combine like terms. And I kind of know what order I want to write these things in. So I'm going to use that to my advantage. I want to write the constant first. So minus 38 when I combine those plus a 9i. So like I said, this is like just like a distribution problem like we had with x's. You have that middle term that usually there are like terms. We can combine this to another number. The extra little step is that we have to swap this I squared to a -1. So don't let anything be over a single power of I, basically. And now that it's a -1, it swaps the sign of my 18 to -18. I have a -20 and a -18 give me minus 38. And the last one that we're doing in this section, well, or the last one that we're doing that is like multiplication. 3 plus 4i squared. So I talked about this, but if you see it 3 plus 4i, you better write this thing out twice. So I have this thing written out twice. I'm doing the same thing as the previous step. 3 times 3 is going to give me 9. This is going to give me plus 12i. And then I'm going to have a plus. Someone help me out here.
What, 16i squared?
Yeah.
Oh, okay, sorry about that. I skipped.
Yeah,
Plus
there should-
12i.
there
When
should
I
be
see
another-
that there's two identical ones like that, I always just take, I
multiply
do
it by
the first. One, yeah, multiply by 2,
2.
yeah.
Yep. You can just double it. Yeah, that's something you can do. So 9 plus 12 and 12i are going to give me the 24i. And I'm going to go ahead and do this plus 16. And I don't want to write that I squared. What am I going to do here?
-1.
Minus 1. So 9 plus 24i. And now this is like a -16. So -16 and 9 are going to give me, overall it's negative. And I think it's a 7 plus 24i. So it is like almost well, it is exactly the same as multiplying a variable, except we add this extra little step of make the I squared a -1. And we make the I squared a -1, then this thing no longer has any i's on it. That might be another thing you notice. Like we had i's on it here. When we get to the I squared, it's like a constant now. We're adding constants to constants. Any questions about these or the approach that we're taking? Okay. So now we got to talk about higher powers. We haven't done this. This was not in the notes. So if we start with I is just an I. Or you could say it's the root of what? -1, something like that. I squared is the thing that when we square it, it is going to be a -1. If we think about I to the third, there are a few ways you can break this up. But it's like an I squared with another sort of I attached. So this is going back 2 plus 1 will give me the 3, right? And so if I think about it like this, I squared is just a -1. So -1 times I is just a -I. So I start with I, which is just I go to I squared. I go to I third, which is really just like a -I. I go to I to the fourth. And there are probably a few ways you can break this up. But if I do I squared by I squared is a -1, and this is a -1. So what is this giving me?
+1.
This is giving me a +1. So let me recap and let me clean this up maybe a little bit. But I would just say is I. I squared, I can tell you, is a -1. I to the third is like a -I. I to the fourth is like 1. And so now I want to think about higher things over here. I to the fifth. There is probably a really smart way to break this up. And there are probably a few ways. But if I think about this as I to the fourth with an additional I, well, this is just 1 times I. We're back to I now. And I can do the same thing with like I to the sixth. I can do I to the fourth times another 2 I's. This is just like 1 times I squared. This is just giving me I squared. I to the seventh. How would you do that?
I to the 5th times I squared? Or I to the 6th times I?
I would keep it with I to the fourth, because that's a good even 1 that we can kind of take out of things. Right? I to the fourth times I to the third will just give you I to the third, which is a -I. And so we have this sort of pattern. We go from I to -1 to -I. Did I write that? I write the pattern over here. And so I is I squared is -1, I to the third is -I to the fourth is like 1. I to the fifth, we're back at I to the sixth, we're back at -1. I to the seventh, we're back at -I. I to the eighth,
Back to 1.
we're back to 1. And so it's got this sort of repeating pattern that you might notice. I to the ninth, I can think of it as I to the eighth with an additional another I. We're back at I. So it is going to have this sort of repeating pattern. And you might notice it repeats how many? Every 4 things, I think is what it's saying. And we're back at 1. So there, if you want to think about this pattern, fair enough. But there is a sort of easy way to get at it. If we want to know what the I is going to be equal to, you might notice things that look like 4, 8, 12, 16, right? 20, 24. These are all things that are going to be 1. You might notice they all divide evenly by 4. They're all multiples of 4. So if we think about this, and there is a little bit of justification. I don't know, I to the 101, and I want to take a square root. Well, not square root. I don't know what I'm doing anymore. If I want to do I to the 101, and I want to know what I to the 101 is going to be equal to. every 4 it's going to be 1. So the thing that I wanted to do, this is what I was trying to write. Trying to write a division bar, and I ended up writing a radical in my mind for some reason. 101, sorry. I would divide it by 4, so I can have like 25 of these things is going to give me 100, and I'm going to have a remainder of 1. And so if I really wanted to do it, I could use my exponent rules, and I'm going to have like I to the 4th 25 times, and I'm going to have an I to the 1 like out here. So this 25 is telling me how many like I to the 4th I have, is one way to think about it. And this remainder is giving me how many I'm going to have out here. But what I know is I to the 4th is just a fancy way to write the number 1. And so this isn't actually doing anything. It's just 1 over 125 times. If you really want to go 1 times 1 times 1 25 times, good for you. But if I want to know what I to the 101 is, it is the same thing as just I to the 1st. And I'm getting that from my remainder. So the quick way to do these things is to divide them by 4. And part of that reason is because every 4, we're going to get a 1 out of there, basically. And whatever the remainder is when we divide it by 4 is where it's going to kind of end up on this sort of thing. So if we have a remainder of 1, we're going to have I to the 1st. Looking along here, I to the 1st. What should this thing equal? So I take 41, and what am I going to do with this thing?
Divide by 4.
And then we divide by 4. I'm going to get 10. One remaining. What's the important thing there that I really want to look at?
The remainder.
The remainder is really the important thing. So this thing is just going to give me 1 repeated over and over, basically, is what this is saying. I'm going to have 10 I to the 4th 10 times. I'm going to be multiplying 1 10 times, and then this is going to be what's left. So this is I to the what power?
One.
Right. This next thing is I to the 66. So same approach. I'm taking 66, and what am I doing with it? Not everyone at once. I'm dividing by 4. So if I divide 66 by 4, I get 26. And then what? 6 is going to give me 24. I'm going to get a remainder of 2. And so what does that tell me about this thing? This thing I can simplify to what? I to the what power?
Second.
Yeah, so it should be I to the 2nd. And really, if you give me anything over I, you should probably simplify that as well. So I to the squared is the -1. So if we give you I to the 66, that's just -1. And so the last one, 128. If I'm looking at 128, and I divide 128 by 4, I'm going to get 3 out of this thing. It's going to give me 12. I'm going to get 2. It's going to give me 8. So what you might notice here is that my remainder here is going to be 0. So if I don't have a remainder, and maybe you could write this as like a I to the 4th to the 32nd, right? If I do 32 times 4 gives me back to 128 is what I'm kind of saying. What is this going to be equal to overall? If the remainder is 0.
That would make it an I to the 4th, right?
Okay, so an I to the 4th, which is just a really fancy way to write 1. So it's just going to be 1. And then I hope this goes back to what we're talking about. I to the 0 also, right? We were talking about things to the power 0 are 1. So it means it divides evenly into 4, right? If it's a multiple of 4, it's just going to be 1. That's another way of saying that. Okay, so I think that's the final problem we got from the homework.
We still have 413.
Do we? Yeah, we skipped over it, huh? That's not in here, huh? 413.
Yeah, it's not part of the actual problems that are listed. The ones that we print out have a different set, but it's the square root of -75 plus the square root of -48.
What we said? Is this what you said?
Yep, that's it.
Okay, so this is 413. So this was not on there. Sorry, I missed it. I thought I had all the problems checked off. I guess I missed one. So they want us to simplify these and to write them out. So if we want to simplify things, what's the first sort of thing we should probably do with these? If you're crunching these. This is the thing I'm seeing here.
Yeah.
Pluck out your eyes. So right away, I'm just going to do that. That should be like your first order response. Pluck out your eyes. Okay, fair enough. I got my eyes plucked out. 25 or 75. Is there an even root that goes into 75? Sorry. Probably give that away a little bit, but
5.
yeah, I can go 5. So I can go 25 into this. 25 and what? 3 will give me
3.
75.
Hmm.
And I think what? Probably something in 3 with this one, right? 3 and 16, I think, give me 48.
Yep.
Okay, I like this one. This is a good one to do. I'm glad you called me out on skipping it. This is 5, and there is a
3.
Yeah, a root 3. So there's a 5, there's an I, and a root 3 on this thing is what I'm seeing.
Mm-hmm.
This is plus
3i over 16.
a what?
3i square root of 16.
Whew,
Oh,
I
hold
think
on,
you're
man.
doing
I
that one.
missed that.
This square root of 16 should give you
4.
4i.
Sorry, not 4, 2. Because
Should
4
be-
can be broken down to 2, right?
Square root of 16 will give you 4.
Right.
Yeah, and then we have an I, and we have a root 3 here.
Right.
Now I got to look at this thing. Can I combine these? Or not?
Yeah.
Simplify this all. So what tells you can combine it is that
Well,
this thing has to be exactly the same thing as that, right? So it is the same power of I, it is the same radical, it is exactly the same thing. So if you wanted to, you could even like think about this as being an x and this being an x, and this is like 5x plus 4x then. But they have to be exactly the same is part of what they're trying to get at here. 5 plus 4 will give you 9. Have an I and I have a root 3. So we can combine them, but they have to be exactly the same. If those radicals were different, it would be a no-go, right? I radical 2. We would not be able to combine these because the radicals aren't the same, right? They have to be exactly the same. So they have to be like terms. And we talked a little bit about like what like terms mean and what they don't mean. Because 2 is not 7. And 7. Any questions of anything we've done? Want to go look back at anything else? It is 10:20 right now, so it is time if y'all need to bounce.
I think I'm pretty good today. Thank you.
Okay. Yeah, we will continue more radicals tomorrow, talking about cube roots and more simplifying stuff. And I need to double check my video is loaded. Stop.